Okay, I hope that exercise helped. Now, of course, I know you have a burning desire to find out how do we find these compositions? How do we know that there's so many grams of this element, so many grams of that element in the compound? Well, speaking of burning, I'm going to show you one such method. It's actually called combustion analysis. It was originally developed by a scientist that is sometimes called the father of modern chemistry, Antoine Lavoisier. And he used this apparatus back in the day when they had to use ovens and all kinds of stuff. And the analysis method was improved, but essentially it was all improvements on the original methods of Lavoisier. Now, let me show you a sketch here of how the process works. First of all, this is a process that is typically used for compounds that are flammable. In other words, you can burn them. Burning is something we observe when we, light fire to things, but in chemistry, we call that a combustion reaction or a combustion process. It involves mixing oxygen with the substance, hitting with a spark, and allowing the whole sample to burn. When we burn compounds that contain carbon and hydrogen, the products are going to be always water and carbon dioxide. This is for example, what happens with gasoline in our cars. Our gasoline is made of a mixture of different compounds that have different proportions of carbon and hydrogen. And when we combust them in the engine, all of that carbon and hydrogen is converted into water and carbon dioxide. In the process, we can do the following. In the Lavoisier apparatus, what you have is you put a tube that has a substance that is able to absorb water. And you run your products of the combustion through there so that all of the water product is absorbed in there. The rest of the exhaust is then passed through a substance that absorbs carbon dioxide. And then anything that did not get absorbed is passed through. The apparatus is set up so that we know what was the starting mass of the material that absorbed the water. So we can calculate the difference before and after combustion and therefore obtain how much water was produced. In the same way, we have a pre-weighted amount of the carbon dioxide absorber. And so the difference between after and before combustion excuse me, gives us the amount of carbon dioxide that was produced. That by itself is not sufficient. Remember, we added oxygen when we carried out the combustion. So the oxygen in the water and the oxygen in the carbon dioxide products, not all of it came from our samples. Some of it was incorporated from the oxygen that I pumped into the combustion chamber. However, because the combustion chamber only had my sample and the input of oxygen, that means that the hydrogen in the water product and the carbon in the CO2 product both came exclusively from our sample. Okay, so that's the strategy here. Let's look at a sample problem here. And again, I apologize if you have not been able to update your notes and this might not have made it there. Just take a moment to write it down. Let's say I start with 11.5 grams of an unknown compound that I know is made of carbon, oxygen, and hydrogen. Combustion analysis yields 22.0 grams of CO2 and 13.5 grams of water. What is the empirical formula of the compound? Remember that in combustion, the compound's components combine with more oxygen. Okay, so one of the tricks here is going to be able to find out, well, how much oxygen was in my original compound. All right, so let's go to our paper and work it out from there.
Okay, so hopefully we understood the strategy of combustion analysis. we start out with a known mass of a compound. All we know is that it has carbon, it has oxygen, and it has hydrogen. The combustion process combines oxygen in with the compound, and that means that at this point we would not know how much oxygen is in the compound. But if there's one thing we know is this: whatever carbon was in the compound is now in the carbon dioxide, and whatever hydrogen was in the compound is now in water. So let's calculate how much carbon is in 22.0 grams of CO2 and how much hydrogen is in 13.5 grams of H2O. And then we're going to apply a friend of ours, the law of conservation of mass, to calculate how much oxygen was in there. Okay, so let's start with the carbon here. Let me do it over here in the bottom. So we're going to start here with carbon. And we're going to say that at this point we have 22.0 grams of CO2. And we had to first of all convert this all to moles. So I went ahead and did a previous calculation here and found that 1 mole of CO2 is 44.01 grams of CO2. So I already did that, and that cancels out the grams of CO2. So now I have how many moles of carbon dioxide are in here. But I know that in 1 mole of carbon dioxide, there is 1 mole of carbon, right? Because there's 1 atom of carbon in 1 molecule of CO2. So 1 mole of C for every mole of CO2. And that's going to cancel out the moles of CO2. And then, now that I know how many moles of carbon are in here, I can calculate how many grams, because I know that there are 12.01 grams of carbon in 1 mole of carbon. And that will cancel those out. So now I can find out all of the grams of carbon in CO2 were originally in my compound. So I can do this calculation, and it comes up to about, when I round it, 6.00 grams of carbon. So that means that in my 11.5 grams of compound, there were 6.00 grams of carbon. Okay, let's look at hydrogen now. You guys probably know how to do this, but I will just write it out for you. We have 13.5 grams of water and 1 mole of water. We can calculate that to be 18.02 grams of water. Cancel the grams of water out. Now careful with this one. How many moles of hydrogen are in a mole of water? That's right, it's 2 moles, right? Because 2 hydrogens per molecule. So there's 2 moles of H in 1 mole of H2O. And that cancels those out. And now we can calculate the mass. We know that there is 1.01 grams of H in 1 mole of H. And that'll cancel out the moles of H. And now I know how many grams of hydrogen are here in this amount of water. But remember, all of that hydrogen came from my original compound. So we can do this. It comes up to 1.51 grams. Again, I'm keeping the sig figs that were given to me by this input number here. Remember that the moles are counted, so they don't count. We don't consider them for the sake of sig figs. But now what we know is that in 11.5 grams of compound, there were 6 grams of carbon and 1.51 of hydrogen. What's the rest? Well, by conservation of mass, everything that you started with should be there when you finish. Now, we cannot identify where the original oxygen went. Some of it may be part of these compounds that were produced. Some of it we have actually just converted into molecular oxygen and left the chamber. So what we know is because of conservation of mass, we know that X grams of oxygen plus 6.0 grams of carbon plus 1.51 grams of H. I'm sorry, I kind of like lost my place here a little bit. Let me roll this paper a little bit here. There you go. 1.51 grams of H should be equal to 11.5 grams total. And that means that X here equals 4.0. Notice that because this number only had one decimal in it, and this is a addition subtraction, we had to bring it back down to one decimal, and that would be 4 grams of O. So essentially now what we have is we have the composition of that sample of compound. And now it's a matter of going back to the way we did things earlier. Let me roll up the paper a little bit here so we can see the bottom of this page here a little better. And now we're going to calculate our composition and therefore our empirical formula. So for carbon, we have H and we have O. We said 6.00 grams, and there's 1 mole is 12.01 grams. Now, if you have one of those calculators that have multiple memory slots, you could have basically gone all the way through here. Remember that at this third step here, we have the moles of carbon already. So you could have saved that in memory and not have to do this calculation here, but I don't have that ability in my calculator, so I'm going to have to do it again. Okay, so this is going to come up to 0.500 moles of carbon. This one is 1.51 grams. And again, 1 mole of hydrogen is 1.01 grams. And that gives me 1.50 moles of H. And then O would have, we found out, 4.0 grams. And of course, 1 mole of atomic O is 16.00 grams. And that comes up to be 0.25. Notice that at this point, what we need to do is find out what the ratios are. So we're going to divide by the smallest of these, which is 0.25. So C over O would be 0.500 divided by 0.25. And that's 2. And then H divided by O would be 1.50 divided by 0.25. And that's 6. And then, of course, O over O equals 1. So that means that our empirical formula would be, and again, I like to write it in the order C, H, O. So it'll be C2, H6, and O. That would be the empirical formula of this compound. As you can see how for compounds that are made of mainly carbon and hydrogen, you can use this type of combustion analysis to figure out what the empirical formula is. Now, I'm going to add something else to this, and we're going to do a little extra step, a little beyond what the exercise required, because I want to introduce us to how can I find then the actual molecular formula of the compound. So we'll be right back. So in the combustion analysis, we found that the empirical formula of our unknown compound was C2H6O. Now let's say that we have a method by which we can determine what the molar mass is. And it turns out to be 92.2 grams per mole. what we can do is we can use these two pieces of information to find the actual molecular formula. Remember, the molecular formula is the one that tells us exactly how many atoms of each element are in this compound. So let's do this. Let's take this formula we have here. What would we predict as the molar mass here? Predicted molar mass. Well, it would be, of course, we have C, we have H, and we have O, right? So we would have 2 moles of carbon, 6 of hydrogen, 1 of oxygen. And we know that carbon is 12.01 grams per mole. Hydrogen is 1.01 grams per mole. And oxygen is 16.00 grams per mole. So if we do this calculation and we run it on the calculator and we add it all up, it comes up to 46.08 grams per mole. This would be the predicted molar mass if the compound actually has the same molecular formula as its empirical formula. But notice that it gives us 46.08, but what we found out was that experimentally determined molar mass was 92.2. So what we do is we take the real, actual, determined value and we divide it by the predicted one. And that would be then 92.2 divided by 46.08. And you can do this in your head. You realize that it's almost 2. In other words, whatever this compound is, its molecule is kind of like if you had this guy duplicated. So therefore, that means that our molecular formula is as if we had taken our empirical formula, and we had 2 of those, or C4H12O2. That is our molecular formula. So you can see where between composition analysis, which in this case was derived from combustion analysis procedures, and knowing the molar mass, we can arrive at the actual molecular formula of the compound. In your lab activities, you're going to learn other methods for determining composition, and we're also going to learn methods for determining the molar masses of different kinds of compounds. So you'll be very equipped to carry out and to do these kinds of problems. All right, so let's go back to our slideshow.
Okay, I hope that helped. And here is one more practice problem. Commercial bleaching agent, you can see there the box on of the product here, has the following composition: 28.93% potassium, 23.72% sulfur, and 47.35% oxygen. The experimentally determined molar mass is 270.0 grams per mole. And by the way, some of the experiments we're going to be carrying out in our lab activities have to do with determining molar masses of different kinds of compounds. So please be patient, and at some point we'll learn some of the methods that we have for determining this. Question 1, what is the empirical formula? Question 2, what is the molecular formula? Now what I'm going to do in this exercise is different from the one we did before is I'm going to turn it around. Since I already know what the molar mass of the compound is, I am going to start by directly finding the molecular formula, And then I'm going to take that and simplify it to the empirical formula. So you can see that you can go in both directions. We're going to go to our paper for this, okay? I'll see you soon.
Our goal in this problem is to find the empirical and then the molecular formula for this compound. It's a bleaching agent. Now, in the previous exercise, the way we did it was, this was the method that we use, I'm going to call it method 1, was to use the composition to find the empirical formula first. So we first find the empirical formula. And then, from knowing the molar mass, we can figure out how many times does the empirical formula fit into a formula that will match the molar mass. And that's how we found the molecular formula. And you can do it this way. Now I'm going to show you an alternative, which is to actually first find the molecular formula and then from there simplify to get the empirical formula. Remember, when we took percent composition, we said, let's assume that we have 100 grams of compound. Let's assume that we have 100 grams of compound. But what if we, instead of ending there, we say, well, what if I had actually a mole of compound? Okay, so what I'm going to do here is I'm going to call this method 2, which is going to be find the molecular formula first. We're going to find this one first. So let me give you, I'll give you one of the steps and then I'm going to leave it there and let you guys finish up, because I think by this point in time, you guys should be in a good place. All right. So let's take potassium. Again, don't forget, percent means parts per 100. So I know that I have 28.93 grams of potassium in every 100 grams of my compound. I'm going to just put a COMP to represent it. Well, here's what I'm interested in. I want to know how many moles of potassium are in 1 mole of compound, because that's what the molecular formula is. So let's go ahead and say that 1 mole of K is, periodic table, 39.10 grams of K. So this step tells me how many moles of potassium are in 100 grams of compound. But what I'd like on the bottom would be the moles of compound. What can I use as a conversion factor? Well, we've used it before. It's the molar mass. They're telling us that the molar mass is 270. So in 270.0 grams of compound, that's 1 mole of my compound. And since I have those units in here, I can cancel them out, and voila, this is going to yield the moles of potassium per mole of compound. When I do this calculation, actually I get 1.998 moles of K per mole of compound. See? So I already know that in a mole of compound, there should be, pretty much 2 moles of K. Okay? So I'm not going to do the rest of them. I'll let you do the sulfur and the oxygen. But I'm going to say here, etc. And I'm going to find out that my molecular formula, if I keep doing this, if I do that same thing now for the sulfur and then for the oxygen, my molecular formula would be K2S2O8. And now I'm going to simplify to get the empirical formula. And the empirical formula, if I simplify this by dividing everything across by 2, would be KSO4. If I had used the first method, I would have arrived from the percent composition to this empirical formula, KSO4, and then I would have had to realize that that is roughly about half of what the molar mass should be, so I would have had to multiply times 2 to get the molecular formula. Again, like I said, I'm skipping the steps here for finding sulfur and oxygen, but I'm pretty sure by this point you can do it yourselves, okay? So this is an alternative method. If they give you the composition and already the molar mass, you can first calculate the molecular formula and then simplify to get the empirical formula.
Chapter 3 of our TRO textbook, I believe, ends with a section on organic compounds. And in some editions, it's section 3.11. Not exactly sure if it's the same number section in all. It doesn't matter. We're going to skip this section. You are not responsible for this. Of course, if you want to read it, that's fine. But in terms of our first exam and in terms of our learning objectives, this is not part of our requirements. So we're going to skip this. Okay, this concludes our presentation of compounds. In our next unit, we're going to tackle now what are the changes that compounds and elements can undergo. In other words, we're going to talk about chemical changes and specifically chemical reactions. So I'll see you soon. Thank you so much.